Hi, hello. For this video, we will be discussing error detection and correction. Okay, networks must be able to transfer data from one device to another with acceptable accuracy. Okay, so a system must guarantee that the data received are identical to the data that has been transmitted. So anytime data are transmitted from one point to another, they can become corrupted, or there might be some errors. Okay, so there are many factors that can alter one or more bits in a specific or in a certain message. So some applications require a mechanism for detecting and correcting errors. Some applications can tolerate a small level of error. Okay, so for example, just a random error in audio or video transmission may be tolerable. Okay, so it may be considered acceptable. However, when we talk about digital, so when we talk about text, we expect a very high level of accuracy. Okay, so this is where error detection and correction comes to place. So to start with, we have here the types of errors. Okay, so as an introduction, we will be discussing some issues that may be directly or indirectly related to error detection and corrections. Okay, so one of them are the types of errors. Okay, so whenever bits flow from one point to another, they are subject to unpredictable changes because of interference. Okay, so when we say interference, when we have interference, this can change or alter the shape of your signal. Okay, so when we say data unit, okay, so we have here in the different types of errors. So we have the first type, which is a single bit error. So this means that only one bit of a given data unit is changed from 1 to 0 or from 0 to 1. So remember, since we are talking about digital informations, okay, so we're talking about binary, so therefore our we only talk about zeros and ones. So whenever your ones is changed to zeros, or your zero is changed to one, so we already represent that to be an error. Okay, so when we talk about data unit, okay, so depends, your data unit can be in the form of a byte. Okay, so it can be in the form of a character or in the form of a packet. Okay, so we have here single bit error, and then we have what we call the burst error. So when we say burst error, we have two or more bits in the data unit. Okay, so when two or more bits in the data unit have changed from 1 to 0 and from 0 to 1. Okay, so the number of bits affected depends on the data rate and the duration of the noise. Okay, so between single bit error and burst error, it is the burst error that is most likely to occur, okay, in a digital transmission. Okay, so the reason is because the duration of the noise signal is normally longer than the duration of a single bit. Okay, so which means that when noise affects your data, it affects a set of bits. Okay, so not just a single bit. So for example, we are sending data of 1 kilobit per second. So we expect a noise of 1 all over 100. Okay, so 1 over 100 seconds. So it can affect up to a maximum of 10 bits. However, when our data is already large, okay, so for example, we have a 1 megabit per second data, 1 Mbps data, that same noise can affect up to 10,000 bits. Okay, so the number of bits affected really depends on the data rate and of course the duration of a specific noise. So if you're going to look at the figure, okay, so if you're going to look at the figure here, you can see an example of a single bit error. So the first figure represents a single bit error, while a second bit a second the second figure represents a burst error. Okay, so it is two or more bits. Okay, so it may be consecutive, or it can also be in a different position. So it may be consecutive or in a different positions. Okay. So we have here another term. Okay, so that is somehow related to our topic for today. So we have here redundancy. Okay, so what do we mean by redundancy? So actually, redundancy is the central concept of detecting or correcting errors. Okay, so to be able to detect or correct errors, we need to send some extra bits in our data. So it is not enough that we just send your original information. Okay, so that that uh, that extra bits, okay, those extra bits, it's is what we call the redundant bits. Okay, so these redundant bits are added by the sender, and it is being removed at the receiver because uh, it is not a part of your original information. Okay, so the presence of redundant bits allows the receiver to detect or to correct corrupted bits. Okay, so we keep on mentioning error correction and detection. So what is the difference between the two? Okay, so we have here detection versus correction. Okay, so actually correction of errors is more difficult, okay, than detecting the errors. Okay, so for error detection, so we are only looking to see if there is any error. Okay, so it can be either a single bit error, so it is just the same. So detecting a single bit error is just the same as detecting a burst error. Okay, so in error detection, the answer is simply yes or no. So do you have an error? So it's just answerable by yes or no. Okay, so we are not even interested in the number of corrupted bits. So we're not even interested if it is a single bit or if it is a burst error, or even how many. Okay, so how many or where are those corrupted bits being located at the specific transmitted data. Okay, so that is what we mean by error detection. Okay, so in error correction, so we need to know the exact number of bits, okay, that are corrupted, and more importantly, their exact location in the specific message. Okay, so the number of errors and the size of the message are important factors in error correction. Okay, so if we need to correct a single error, for example, in an 8-bit data unit, we need to consider 8 possible error locations. Okay, so where among those 8 bits are or is the error being located. Okay, so if we need to correct two errors in a data unit, for example, of the same size, let us say of 8-bit, we need to consider 28 values, okay, or 28 locations. Okay, so where did your 28 came from? So if you're going to remember in your statistics, I think, so the permutation, okay, so permutation of 8 by 2, that will give you 28 possible combinations. So if you have two errors in an 8-bit data stream, okay, so imagine the receiver's difficulty if we have more bits being considered. Okay, so for example, it is very difficult finding 10 errors. Okay, so finding 10 errors plus their exact location in a data unit of 100 bits. So that is a permutation of 100 to 10. Okay, so that will give you so many possible locations or combinations, combination of locations of where your error might be located. Okay, so that's the difference between detection and correction. Okay, so one thing more, another important topic in error correction and error detection and correction is coding. Okay, so what do we mean by coding? So Usually, the sender adds redundant bits through a process that creates a relationship between the redundant bits and the actual data bits that is being transmitted. So in coding, so redundancy is achieved through various coding schemes. Okay, so how are you going to add, or how are you going to apply the specific redundant bits to your original information? Okay, so the ratio of the redundant bits to the data bits and the robustness of the process are very important factors in any coding scheme. Okay, so the receiver checks the relationship between the two sets of bits to be able to detect your errors, the actual bit and the redundant bit. Okay, so there are two particular coding schemes categories. So we have what we call the block coding and the convolution. Okay, so in this topic, or in this presentation, we are just concerned with the block coding. Okay, so the second type, which is convolution, is more complex. Okay, and it is beyond our discussion, or beyond our scope. So we will be concentrating on block coding. Okay. So in block coding, so let us now go to block coding. We have several terms. Okay, so to keep in mind. First is a data words. Okay, so what do we mean by data words? Usually this divides messages into blocks, okay, each with k number of bits. Okay, so with specific k number of bits, using 2 raised to k, so those are the numbers. Okay, so those are how many data word combinations that we are going to produce. Okay, so when we have k bits, okay, for example 8 bits, so it becomes 2 raised to 8, or for example we just have 5 bits, so it will become 2 raised to 5. So those are the number of data words combinations that are possible. Okay, and then we have another term, which is code words. Okay, so code words, uh how do we form the code words? So we usually add R, okay? So R redundant bits to each block to make the length equivalent to N is equal to K plus R, okay? So since we have already added R, so we have formed several code words, okay? So how many code words are possible? So we have 2 raised to N. Okay, so we have here since you're n now. Okay, so by looking at the uh, presentation, so n will always be greater than your k. So therefore, the number of possible code words is always larger than the number of possible data words. Okay, so block coding process class is, we can say this, one-on-one. Okay, so a data word must be included in a specific code words. Okay, but since your n is greater than your k, so we have here 2 raised to n minus 2 raised to k. So we have here 2 raised to n minus 2 raised to k. So the difference here is not an original information. It is not an original data. It is not an original data word. Okay? So therefore, usually 2n minus 2k, they are not being used. Okay? So that means we can use those unused or invalid codes for error detection, and also for error detection. Okay? So block coding process, which I've mentioned a while ago, is a one-on-one process. That means the same data word is always encoded as the same code word. Okay? So the difference between 2n minus 2 raised to n minus 2 raised to k is invalid or illegal, or they are not used. Okay? So there are no data words that can or that was used in that specific values. Okay? So in the error detection, the existence of these invalid codes, if ever the receiver receives an invalid code word, this indicates that the data was corrupted during transmission. Okay, so that will be an indication, that will be an example of error detection, that if a certain receiver receives a code word within these specific values, therefore it is already an indication that the data was somewhat corrupted during your transmission. Okay, so we have here we have here uh, a figure, okay, or a diagram. Okay, so a block diagram. How can error be detected, okay, using block coding? So we have to remember that a receiver can detect a change in the original code word if we have, or if we satisfy these two conditions. Okay, so number one, the receiver has an the receiver has or can find a valid a list of valid code words, okay, so the different messages that was being transmitted. And number two, the original code words has changed to an invalid one. Okay, so if we if this two is observed, okay, so a specific receiver can detect a change in the original code word. Okay, so the role of a block coding in error detection, or the process of error detection in block coding, is being shown in this figure. Okay, so it says here, so if you're going to look at the figure, the sender creates code words. Okay, so how does the sender creates code words? So the sender creates code words out of data words by using a generator that applies the rules and procedures of encoding. Okay, so we have a generator. Okay, so um, each code word sent to the receiver may change during your transmission. Okay, so in the generator, it is where you apply, or you add additional bits. Okay, so the R bits in the previous slide. Okay, so the output of a generator is your N bits code word. Okay, so each code word is being sent, as you can see in the in the figure. Our transmission is always considered as unreliable. Okay, so if it is unreliable, we can expect noise. Okay, so we can expect errors. So the code word that was sent, okay, in the encoder or by the sender, may change during your transmission. Okay, so specifically when we have an unreliable transmission. Okay, so if the received code word is the same as one of the valid code words that is being listed, so it says there that we have a list of some valid code words. Okay, so if the received code word is the same as one of the valid code words, then that word is accepted. Okay, so we have a checker. So we have a checker there at the receiver side, at the decoder side. So if it is a valid code, so therefore it is being accepted. However, if the received code word is not valid, or it is within this specific invalid code words that was produced, okay, so it was being discarded. Okay, so the checker will be deciding whether to extract or to accept the message, or the code word, or to discard the code word. Okay, so however, okay, if the code words is corrupted during transmission, but the received word still matches a valid, so it's possible. Okay, so although the although the message is corrupted, however, the corrupted message still identifies, or has an has the same valid code words with other valid code words. Okay, we might say that an error remains undetected. Okay, because even though it's supposed to be an error, but it has a valid uh, code word. Okay, so it has a valid code word that looks like it. So therefore, there's a tendency that an error still remains undetected. Okay, so it says there, an error detecting code can detect only the types of error for which it is designed. Okay, so other types of error may remain undetected. Okay, so that is our condition for error detecting codes. So another term that we might consider is homing distance. Okay, so what is a homing distance? So this is the number of differences between corresponding bits. Okay, so homing distance is represented as d, okay, open and close parentheses, x and y. So we are considering two different code words. So code word x represents a code word and y represents another code word. Okay, so the distance between these two code words or corresponding bits is what we call homing distance. So homing distance is one of the central concept in coding for error control. Okay, so um, homing distance between two words of the same we usually consider homing distance between two words that have the same size. So we always get the homing distance if the two words have the same sizes. Okay, so why homing distance is important for error detection? Okay, so what is its importance? So the homing distance between the received code words and the sent code word is the number of bits that are corrupted during the transmission. Okay, so in homing distance, we usually apply the XOR operation. Okay, so in your logic circuits, you have already discussed. Okay, so um, you have already an idea what is an XOR operation. Okay, so the homing distance between two words is the number of differences between corresponding bits. Okay, so how do we uh, apply homing distance for error detection? Okay, so for example, we have a code word. Okay, so for example, we have a code word. So, for example, we have a code word which is equivalent to 0000. Okay, so 4 bits code word. And we have, this is the one which is sent. Okay, and then we have a code word which is 01. Okay, so 5 bits. Okay, so 01101. So we received this type. Okay, so this was the one which was sent, and then this is the one which was received. Okay, so in this type of example, we can easily detect that we have 3 bits that is in error. Okay, so by looking at the figure, we can see that there are 3 bits in error. Okay, and the homing distance between the two. Okay, so what is the homing distance between the two? So that is represented as d. So what is your x? X is the one that was being sent. So that is 1 2 3 4 5, and then received is 01101. Okay, so our homing distance is equal to 3. Okay? So, we will just count the number of ones in the result. Okay? So, how do we get the result? We just XOR the sent and the received messages. Okay? So, how do you XOR? 1, 2, 3, 4, 5, 0, 1, 1, 0, 1. Okay? So, using the XOR operation, we have when you have 0 or 1 or 1 or 0, so the result is 1. Okay, so the result is 1. So if you have two zeros, so that is equal to 0. So 0 and 1, that is equal to 1, 0 and 1, that is equal to 1. And when you have two zeros or both ones, that is equivalent to 0. Okay? So for this type of Hamming detection, all you have to do is to count the number of ones in the result. So how many number of ones do we have? So we have 1, 2, and 3. Therefore, the Hamming distance is equivalent to 3. Okay? So therefore, there are 3 errors. There are 3 errors in your sent and received information. Okay? So Hamming distance, always remember you have a value that is greater than or equal to 0. Okay, so if it is 0, if you don't have any 1, so therefore we didn't detect any error. Okay, so we have here how to find. Okay, so how to find the minimum Hamming distance if we want to detect up to S errors. So we have here the minimum Hamming distance for error detection. So the smallest Hamming distance between all possible pairs of code words. So the minimum Hamming distance for error detection is the smallest Hamming distance between all possible pairs of code words. Okay, so if S, for example, our error is S, okay? So how do you find the minimum Hamming distance if we want to detect up to S errors, okay? S is equal to 1 if you want to detect 1 error. S is equal to 2 if you wanted to detect 2 errors, and so on, okay? So if S errors occurs during transmission, the Hamming distance between the sent code word and the received code word is S, okay? So to guarantee the detection of up to S errors in all cases, the minimum Hamming distance in a block code must be equal to, so we just write minimum, okay? So Hamming distance is D. So to get the minimum Hamming distance requirement for error detection, so we just write there minimum. So D minimum must be equal to S plus 1, okay? So that the received code words, so it is S plus 1, so that the received code words does not match a valid code word. Okay, so in other words, if the minimum distance between all valid code word is S plus 1, the received code word cannot erroneously mistaken for another code word, then error will be detected. Okay, so although D mean, which is equivalent to S plus 1, may be able to detect more than S errors in some special cases, only S or fewer errors, okay, may be guaranteed to be detected. Okay, so for example, we have here your an example of a data word. Okay, so upon passing through a certain generator, okay, so we add one redundant bit, okay, so from 2 bits data word, it became 3 bits data word. So therefore, our n here is equal to 3 and our k is equal to 2. Okay, so the minimum Hamming distance for our first code, okay, so first code scheme is 2. Okay, so for example, if we check, okay, so if we check this different code words, okay, so all we have to do is to count the number of ones. Okay, so the minimum Hamming distance for our first code scheme is 2. So this code guarantees detection of only a single error. Okay, so there can only be a single error guaranteed if we have our minimum Hamming distance equivalent to 2. For example, if the third code word, okay, our third code word is 101 is sent and one error occurs, okay, so the received code word does not match any valid code words. Okay, so that is what we mean by that. So if 2 error occurs, however, the received code word may already match a valid code word and the errors are not being detected. Okay, so for example, for 101, for example, so for 101, if only one bit is if only one bit is, what do you call this? If only one bit is an error, so let us say only this one, okay? So it will become 1, 0, 0. So as you can see, you cannot see any bit there or any valid data code there that is equivalent to 1, 0, 0. So for example, only the center, okay? Only the center, only the middle bit is will be an error. So this will become 1, 0, 1. So if the middle bit is an error, so this will become 1, 1, 1. So as you can see, there are no valid errors or there are no valid code words that is equal to 1, 1, 1. However, if there are two, okay, so let us say two bits that will change or will produce an error. So let us for example say 101. So let us say this middle, so this second and last will experience an error. So this will become 1, 1 and 0. Okay, so 1, 1 and 0 is considered as a valid code word. So therefore it cannot it may pass. Okay, it may pass as a valid code word, although in reality there is already an error. So that is what we mean by Hamming distance. Okay, so for for um for Hamming distance, which is equal to 2, we can only detect one single error for that. Okay. Okay, so we have here linear block codes. Okay, so what do we mean by linear block codes? So this is a code in which the exclusive or addition modulo. So the exclusive OR is also called the addition modulo 2. Okay, so if you're familiar with that in your logic circuits, okay, so exclusive OR is the same or similar to the addition modulo 2 of two valid code words which creates another valid code words. Okay, so if we XOR, okay, if we XOR two valid code words, it will create another valid code word. Okay, so if that is the case, we call that a linear block codes. Okay, so almost all block codes used belong to a subset of block codes that are called linear block codes. Okay, so the use of nonlinear block codes for error detection and correction is not widespread because their structure makes theoretical analysis and implementation very, very difficult. Okay, so uh, although formal definition of linear block codes requires the knowledge of abstract algebra. Okay, so we just have an informal and simple definition. So this is our simple and informal definition for linear block words. Okay, so XORing, okay, XORing the second, for example, so in this, so if you're going to look at the XORing of two single bits or two words, okay, so if you have both zero, so 0 XOR 0 is equal to 0 and 1 XOR 1 is equal to 0, okay, or 0 XOR 1 is equal to 1 and 1 XOR 0 is equal to 1. Okay, so XORing two patterns. Okay, so we will just follow your so this is a review. Okay, so we will just follow this specific review. Okay, so how do we give an example of linear block codes, for example? So in this table, for example, XORing the second and third code words. Okay, so for example, this is our second code word. So our second code word is 0. So our second code word is 011, okay? And then let us XOR that to our third code word, okay? So which is 101. So that is 101. So let us XOR them, okay? So how do you XOR them? So 11, this will give you 0. 10, this will give you 1. 01, this will give you 1. So 110. Okay, so XORing two valid code words can give you another valid code word. So if you're going to look at 110, so 110 is in your valid code words list. Okay, so that is what we mean by linear code words. Okay, so for example, let us XOR the third and the fourth. Okay, so your third is 101 and the fourth is 110. Okay, so that will give you, this is 1, and this is 0. So that is 0, 1, 1. So if you're going to look at your valid code words, we can see 0, 1, and 1. So that is what you mean by linear code words. So when we try to XOR two valid code words, you will be what do you call this? It will result in another valid code word. Okay? So we have here the minimum distance of linear block codes. Okay, so the minimum Hamming distance for a linear block code is the number, just count the number of ones. Okay, so this is just the counting the number of ones, okay, in the non-zero valid code word with smallest number of ones. So you just have to count the number of ones, and then the smallest number of ones will determine the minimum Hamming distance for a linear block word. For example, the number of ones, okay, so the number of ones in the first table, so if you're going to count the number of ones um in a non-zero, okay, so we skip the first code word because there are no ones there, so we just have to count the number of ones in a non-zero code words. So if we count them, we can have a 2. Okay, so we all have number 2, so therefore the minimum distance is equivalent to 2. Okay, so however, for the second table, okay, so if we count the number of ones there, so for the first code word, of course, that is all 0. So for the second code word, we have 3. So you just have to count the number of ones. So that is 3. So for the third, you have also 3. And then for the fourth, you have number 4. Okay, so unlike the first table where we all have number 2s, so therefore our Hamming distance is equivalent to 2 automatically. So in the second table, we have 3 and we have 4. Okay, so what is the minimum Hamming distance here? So the one with the smallest number of ones, and in that case, it is equivalent to number 3. Okay, so our table number 2, we have the minimum, which is equal to 3. So what does this mean? So this code can detect up to 2 errors. Okay, so this code can detect up to 2 errors. So the first table can detect up to 1 error. Remember, you have S plus 1. Okay, wherein S is the number of errors to be detected. Okay, so therefore, in the second table, we see that when any valid code words is sent, 2 errors create a code word which is not in the table of valid code words. Okay, so the receiver uh, can notice that. Okay, so the receiver can detect that. Okay, so that is what you mean by the minimum distance. Okay, next is parity check code. Okay, so what is parity check code? So perhaps the most familiar error detecting code is the parity check code. Okay, so in this case, we have k-bit data word. Okay, so a k-bit data word is changed to an n-bit data code word. Okay, so wherein n is equivalent to k plus 1. Okay, so earlier, it is equal to r. Okay, so because it depends on how many additional bits do we wanted to add, but in parity check code, we only add one extra bit. Okay, so that extra bit is what we call the parity bit. Okay, so the parity bit is selected, so it is selected to make the total number of ones in the code word even. Okay, this parity check code is also under the linear block code. Although some implementations specify an odd number of ones. Okay, so for our discussion, we will be considering even number of ones. Although in some other books or in some other references, you can also consider odd number of ones. Okay, so in parity check code, so the minimum Hamming distance is 2. Okay, why? So because we can only detect, okay, so it has a means, this code has a means of detecting only a single bit error. Okay, so in this type of example, in our table, we have a parity check wherein our k is equal to 2 and our n is equal to 3. Okay. So this is a simple parity check wherein our k is equal to 4 and our n is equal to 5. So if you're going to notice the colored blue, okay? So it can either be a 1 or a 0 depending on the number of ones that are in the data word. Okay, so you just have to count the number of ones and you have to make it even. So for example, if the number of ones is already even, so therefore we will be adding a 0. So but if the number of ones is an add, so that means we're going to add a parity bit which is equivalent to 1. Okay, so for example, our first data word are all 0, so therefore we will be adding 0. Okay, because if we add 1, it will become an add parity. So for the second code word, we have 1 1. Okay, so 1 1 1. So to make that even, so we have to add another 1, so to make the number of ones equal to 2. So therefore we add here 1. Okay, the same is true with the other. So that is how simple your parity check code is. So this is an encoder and a decoder for a simple parity check code. Okay, so we have here a sender and a receiver block diagram for an encoder and a decoder for a simple parity check code. Okay, so the calculation is done arithmetic. Okay, so the encoder uses a generator that takes a copy of a 4-bit data word. Okay, so those are your A0 to A3. Okay, so and generates a parity bit R0. Okay, so it generates a parity bit which is R0 depending on the number of ones in the original data word. Okay, so this creates a 5-bit code word. So from a 5 for from a 4-bit data word to a 5-bit code word. Okay, so the parity bit that is added makes the number of ones in the code word even. Okay, so the sender sends the code word, which again may be corrupted during transmission because of an unreliable transmission. Okay, so in the receiver end, the receiver receives a 5-bit word. Okay, the checker now at the receiver does the same thing as the generator in the sender with one exemption. Okay, so the addition is done over all 5 bits. Okay, so we have here again a modulo 2 addition. Okay, so RO depends on how many ones are present in this um, A3 to AO. So in this case, this is only 4, and for the receiver end, this is equivalent to 5. But um they both have a modulo 2 operation. Okay, so the checker at the so the result, which is called the syndrome. Okay, so the result of the checker is we call a syndrome. So that is represented by S. Okay, so when the syndrome is equal to 0, okay, so this is when the number of ones in the received code word is even. Okay, otherwise it is 1. So therefore, the syndrome is passed to the decision logic analyzer. So if the syndrome is equal to 0, there is no detectable error in the received code word. So that means the data portion of the received code word is accepted as a data word. However, if the syndrome is equivalent to 1, the data portion of the received code word is discarded. So that means that the data word is not created. So all you have to do is to look at the value of S0, SO or the syndrome. So if it is 0, No error was detected. If it is 1, there is an error. Okay, as simple as that. Okay, so next, okay, so after the parity parity bit code, so we have what we call the cyclic codes. Okay, so what is a cyclic code? So if a code word is cyclically shifted or rotated, the result is another code word. Okay, so in this case, if we call the bits in the first word A0 to A6, okay, then the bits in the second word would be B0 to B6. Okay, so we can shift the bits by using the following. So B1 becomes A0, B2 becomes A1, B3 becomes A2, B4 becomes A3, B5 becomes A4, B6 becomes A5, and B0 becomes A6. Okay, so in the rightmost equation, so here in the rightmost equation, the last bit of the first word is wrapped around and becomes the first bit of the second word. So that is your cyclic code. So these are special linear code with one extra property. Okay? So for example, so let's have an example. So for example, we have a 1 0. So for example, we have 1 0 1 1 1 0 1 1 0 0 0. Okay, so for example, we have 1 0 1 1 0 0 0. If this is our code word and we cyclically left shift that, okay, so shifting to the left, so this will become 0 1 1 0 0 0 1. Okay, so in this case, if we do this, we can say that this 011001 is also a valid code word. Okay, so if we shift this first valid code word, so the resulting bits or the resulting combinations is also considered as a valid code word. So that is what we mean by cyclic codes. Okay, so we have here cyclic redundancy check. Okay, so we have here a subset of cyclic codes. So we can create cyclic codes to correct errors. So the theoretical background is beyond the scope of our discussion. So we will just discuss how to make this CRC or cyclic redundancy check. Okay, so we can see both linear and cyclic properties of this code. Okay, so these are the valid data words and then the valid code words, and then we have here the code words. So if we shift this, of course, for example, if we shift this will become 00, so the second, okay, so for the second code word, if we shift that to the left, so for example, its value is the second, so that is 0001 011. So if we happen to shift this to the left, so this will become 0010110. Okay, so looking at the value of this, so do we have a value of this? So we have 0010110, which is your third code word. Okay, so that is the characteristic of your cyclic redundancy codes. Okay, so that is your cyclic codes. So if we continue doing that, we can complete the specific table for your code word. Okay, so we can see that both of this linear and cyclic properties of this code. Okay, so what is the linear property of this code? So for example, let us XOR this 2. Okay, so if we XOR this 2, that will give you 1. This is 0, this is 1, this is 1, this is 1, this is 0, 0. Okay, so looking at the value, so do we have 0, 0, 1, 1, 1, and 0, 1? Yes. Okay, so this is your third code. So this shows the linear characteristic of your coding scheme. Okay, so if you XOR two valid code words, you produce another valid code words. If you shift okay, a valid code word, you can produce also a valid code word. So in this table, we can see the characteristics of both the linear and cyclic properties of this code. Okay? Okay, so this is how CRC, cyclic redundancy checking, encoder and decoder looks like. Okay, so how does it functions, class? So at the encoder side, okay, so the data word has k bits. So in this case, we have 4 bits. Okay, so the code word has n bits. Okay, so in this example, we have 7. Okay, 7 bits. So the size of the data word is augmented by adding n minus k. Okay, so by adding n minus k. So this is 7 minus 4. So that will give you 3. Okay, so the size of the data word is augmented by adding n minus k. So in this case, it is 3 zeros to the right hand side of the word. So the n bit result is fed into the generator. Okay, so the generator uses a divisor of a size n, okay, minus k plus 1. So n minus k plus 1. So in this case, our n is 4. Our k is 4 plus 1. So that means 4. Okay, so in that case, we have here 4 predefined and agreed upon divisor. Okay, so that is your divisor, which is 4 bits. Okay, so this is already predefined and it was already designed, or it was already agreed upon. Okay, so the generator divides the augmented data word by the divisor. So we are going to make use of modulo 2 division. Okay, so the quotient of the division is discarded. So the remainder R2, R1, and R0. Okay, so the remainder R2, R1, and R0 is appended or joined to the data word to create the specific code word. Okay, so that is how you produce the code word. Now, at the receiver end, okay, so at the receiver end, the decoder receives the code word, okay, possibly corrupted again because of unreliable transmission, okay. So a copy of all n bits is fed to the checker, which is a replica of your generator. Okay? So the remainder produced by the checker is a syndrome. Okay? So we again here have a syndrome. So our syndrome is n minus k, which is 3 in this example, bits, which is fed to the decision logic analyzer. So the analyzer has a simple function. Okay? So if the syndrome bits are all zeros, okay, the 4 leftmost bits of the code word are accepted as the data word. So it is interpreted that has no error. Otherwise, if there is a value of 1, if it is not all 0, so the bits are discarded. That means it detected an error. Okay? Okay. So we have here encoder. Okay, so what happens in the encoder? So in the encoder takes a data word and augments it with the n minus k number of zeros. Okay, so it then divides the augmented data word by the divisor. So as mentioned earlier, we are going to make use of a modulo 2 division. Okay, so the process of modulo 2 binary division is the same as the familiar division process we use for decimal numbers. Okay, so however, addition and subtraction in this case are the same in this case. So same for addition, same for subtraction. When you're adding or you're subtracting, we both use the XOR function. Okay, so we use XOR operation to do both. So as in decimal division, the process is done step by step. Okay, so in each step, a copy of the divisor is XORed with the 4 bits of the dividend. Okay, so we have to remember the dividend, the divisor, and the quotient. So the result of the XOR operation, or the remainder, okay, is a 3 3 bits in this case, okay, which is used for the next step after one extra bit is pulled down to make it 4 bits long. So there is one important point we need to remember in this type of division. If the leftmost bit of the dividend or the part used in each step is equal to 0, the step cannot use the regular divisor. So in this case, the regular divisor is 1011. So this is the one which is being agreed upon, okay, or in the design. So this is a predefined values. We need to use all zeros instead as your divisor, okay? When there are no bits left to pull down, we then have the result. Okay, so as you can see, there are no more additional bits here. The remaining number of bits is already equal to 3. So therefore, um, we have to stop there. Okay, so the 3-bit remainder forms the check bits R2, R1, and R0. So they are appended. Okay, so they are joined with the data word. So in this case, our data word is 1001. So the remainder 110 is appended to your 1001, which happens to be the created code word. So that is how you create your code word. So the decoder does the same. Okay, so in the decoder, the remainder of the division is the syndrome. Okay, so if the syndrome is all zeros, there is no error with a highly probability, so otherwise everything is discarded. Okay, so the code word can change during transmission. So this does the same division process as the encoder. So the data word here is separated from the received code word and accepted. Okay, so if there is no error. So the figure shows, there are two figures there. So this shows two cases. Okay, so the first figure is an uncorrupted. So as you can see at the bottom of the computations, your syndrome is equal to 000. If your syndrome is equal to all zeros, therefore that is an uncorrupted value. Okay. However, if you're going to look at the second figure, so your syndrome is non-zero. Okay, so it is equivalent to 011. So therefore, it is discarded, or it means that you have a zero, you have an error. Therefore, because the syndrome is not all equal to 0. So you can see, you can determine or you can detect if there is an error just by looking at the syndrome. Okay, so when your syndrome is equal to all zeros, your data word is accepted. If not, your data word is discarded. Okay, um, so we have here a continuation. So we have here polynomials. Okay, so a polynomial, it represents a pattern of zeros and ones with coefficients of zeros and one. Okay, so uh, the power of each term shows the position of the bit, and the coefficient shows the value of the bit. Okay, so this is a better way to understand cyclic codes. So this is still under the cyclic codes, and how they can be analyzed. So we can represent your cyclic codes into or by polynomials. Okay, so we have here in the figure shows a binary pattern and its polynomial representation. Okay, so the first figure shows a binary pattern, and the second figure shows its corresponding polynomial. Okay, so for the first figure, this shows how to translate a binary pattern into a polynomial pattern. Okay, so um, the number of bits or the position of the bits is the power, okay, shows the power, while the coefficient shows the value of the bit. So it's either 0 or 1. So in figure B, okay, so we show how the polynomial can be shortened, okay, by removing, so we can shorten the value, okay, we can minimize the value by removing all terms with 0 coefficients and replacing your x raised to 1 by and x raised to 0 by 1. Okay, so your x raised to 1 can be represented as x, while your x raised to 0 can be represented as 1. So the figure shows one immediate benefit. Okay, so we can see that from a 7-bit pattern from A0 to A6, so from a 0, so for a 7-bit pattern, it can be replaced by only three terms. Okay, so in that case, from 1 0 0 0 0 1 1, it can be replaced to x raised to 6 plus x plus 1. Okay, so the benefit is even more obvious. Okay, if when we have more number of bits. Okay, so for example, we have a polynomial having a value, for example, of x raised to um 23. Okay, so plus x cube plus 1. Okay, so in this case we can replace a bit pattern of 24 bits in length. Okay, so we have 3 ones and 21 zeros. Okay, so if we represent that in bit pattern, so that will become 24 bits, but in polynomial it is just three terms. So this is the one immediate benefit of using polynomials. Okay, so we have here several terms. So, degree of polynomial. So, what do we mean by the degree of a polynomial? This is the highest power in a polynomial. Okay, so the degree of polynomial is 1 less than the number of bits in a pattern. So, for example, if you have your 7-bit pattern, so the degree is 6. Okay, so if you have a 5-bit pattern, so your degree is 4. Okay, so for example, you have x. For example, you have x raised to 6. Okay, so you have x raised to 6 plus x plus 1. So the degree of polynomial is equivalent to 6. So this is the highest power in a polynomial. Okay, so how about adding and subtracting polynomials? So the coefficients are the adding and subtracting of polynomials in mathematics are done by adding and subtracting the coefficients of terms in with having the same power. So in this case, our coefficients are only zeros and ones. Okay, and we add them using modulo 2 addition. Okay, so what do we mean by modulo 2 addition? So just what we have did in our previous slides. Actually, there are two consequences. Okay, so what are our two consequences? So addition and subtraction are the same. Okay, so since they both make use of modulo 2, so there are no differences between addition and subtraction. And adding and subtracting is done by combining terms and deleting pairs of identical terms. Okay, so what do we mean by that? So for example, okay, so for example, we add, okay, so let's add x raised to 5, okay, plus x raised to 4 plus x squared, okay, and so let's add plus x raised to 6 plus x raised to 4 plus x squared. Okay, so what do we have there? Okay, so it says there that adding and subtracting is done by combining terms and deleting pairs of identical terms. So in this case, when we add them, the answer is simply x raised to 6 plus x raised to 5. Okay, so because x raised to 4 is a same term and x squared is the same term, so we just delete it. Okay, so we just simply delete it. So those terms having the same values are just deleted. However, note that if we add, for example, three polynomials, okay, so for example, we have x2, x squared plus x squared, and another x squared. We get x squared 3 times. So we delete a pair and keep the third one. Okay, so that is how we do it. Okay, so third is multiplying or dividing terms. Okay, so in this arithmetic, so multiplying terms by another term is very, very simple. Okay, so we just simply add the powers. Okay, so for example, if we wanted to multiply x cube multiplied by x raised to 4, so this is simply x raised to 7. Okay, so for dividing, we just subtract the power of the second term from the power of the first term. So let's, for example, we have x raised to 5 divided by x squared. So this will result to x cubed. Okay, so this is how we multiply or divide terms. Okay, so how about multiplying two polynomials? Okay, so this is done term by term. Okay, so each term of the first polynomial must be multiplied by all terms of the second. Okay, so afterwards, the result is then simplified and pairs of equal terms are deleted. Okay, so in this example, for example, we have x raised to 5 plus x raised to 3, x raised to 2 plus x multiplied by x squared plus x plus 1. So we just simply multiply it term by term. Okay, and then eventually you just combine, okay, those terms that has no pair. Okay, so if the terms has pair, so let's take for example 5, you have x raised to 4, you have x squared, so we cannot see that anymore. But if you're going to notice, we have 3x cubed. Okay, so the first pair will be deleted, and then we have one more term left. So therefore, we still have x cubed in our resulting value. Okay, so how about dividing one polynomial by another? So you simply divide the first term of the dividend by the first term of the divisor to get the first term of the quotient. Okay, so you multiply the term in the quotient by the divisor and subtract the result from the dividend. Then we repeat the process until the dividend degree is less than the divisor degree. Okay, so the division of polynomial is conceptually the same as the binary division that we discussed in the earlier cyclic redundancy checker encoder. So we have here next, we have shifting. Okay, so what do we mean by shifting? So shifting is when a binary pattern is often shifted a number of bits either to the right. We can shift it to the right, or we can shift it to the left. Okay, so shifting to the left means adding extra zeros as at the rightmost bits. Okay, so this means shifting to the left is accomplished by multiplying each term of a polynomial equivalent to x raised to m, okay, wherein m is the number of shifted bits. Okay, so for example, you wanted to shift 3 bits to the left, or 2 bits to the left, or so on. Shifting to the right means deleting some rightmost bits. Okay, so shifting to the right is accomplished this time by dividing each term of a polynomial by x raised to m. Okay, so we have here an example. So the following shows shifting to the left and to the right. Okay, so we also like for example, shifting left 3 bits. Okay, so 10011, it becomes 100110000. So you add 3. Okay, so you add 3 bits to the rightmost side. Okay, so shifting to the right, so this becomes 10. Okay, so this becomes 10, or you divide. Okay, so x raised to m. So shifting 3 bits to the right, so it just becomes 10. So 011 was deleted. Okay, so this becomes So this is in terms of bits. So this is in terms of polynomials. Okay. So note that we don't have a negative powers in a polynomial representation. Okay, so we don't do negative powers. So this is your cyclic code encoder using polynomials. Okay, so the divisor in a cyclic code is normally called the generator polynomial or simply the generator. Okay, so this is just like what we did earlier, but this time it is in the form of a polynomials. Okay, so this will show you the creation of a code word from a data word. Okay, so a polynomial version of the CRC encoder that we have discussed a while ago. So this is a CRC division using polynomials. So the process is shorter. If you can see, the process is shorter. So the data word 1001 was represented by x cubed plus 1. Okay, while the divisor, which is equivalent earlier to 1011, is now represented by x cubed plus x plus 1. Okay, so to find the augmented data word, we have left shifted the data word 3 bits. Okay, so multiplying it by x raised to m. So in this case, your m is equal to 3. So x cubed. Okay, so the result is x raised to 6 plus x cubed. Okay, so division is straightforward. We divide the first term of the dividend x raised to 6 by the first term of the divisor x cubed. So x raised to 6 minus x cubed, that is equivalent to x cubed. Okay, then we multiply x cubed by the divisor and subtract the result from the dividend. So the result is x to the fourth. Since x to the fourth is a degree which is still higher than x cubed in the divisor, we continue to divide until the degree of the remainder is less than the degree of the divisor. Okay, so it can be seen that the polynomial representation can easily simplify the operation of division in this case. So this is easier compared with the previous encoder that we have discussed. Okay, so cyclic code analysis, we can analyze a cyclic code to find its capabilities by using polynomials. Okay, so we define f of x, a polynomial with a binary coefficients. Okay, so let's make use of this different coefficients. So when we say d of x, so that is your data word, c of x, that is your code word, generator, that is your g of x, syndrome, okay, so that is your s of x, and then finally we have error, which is e of x. Okay, so if x is not 0, if s of x is not 0 or your syndrome is not equal to 0, then one or more bits is corrupted, or that means there is an error. Okay, however, if s of x is 0, it can either be two ways. Okay, so the first is there is no bit corrupted, or the decoder failed to detect any errors. Okay, so we do not right away conclude that there is already no error that was detected. So it can either be really no error was detected, there is no really corrupted error, or there is an error but it was not detected. Okay, so always remember in a cyclic code, if s of x or the syndrome is equal to 0, one or more bit is corrupted. Okay, but if your syndrome is equal to 0, so it's either no bit was really corrupted, or some bits are corrupted but the decoder failed to detect them. Okay, so this shows the relationship. Okay, so in our analysis, we want to find the criteria that must be imposed on a generator, okay, to detect type of error we specially wanted to be detected. Okay, so this shows the relationship among the sent code word, your error, the received code word, and the generator. Okay, so the received code word is always CX, so C is your code word, plus EX. EX is your error. Okay, so the received code word is the sum of the sent code word and the error. Okay? So the receiver divides the received code by GX or the generator to get the syndrome. So the received code word divided by your GX, or that will become C of X divided by G of X plus E of X divided by G of X. Okay? So in a cyclic codes, those E of X error that are divisible by GX are not usually caught. Okay, so the first term in the right, so that is your CX all over GX of the equality has a remainder of 0. Okay, so so the syndrome is actually the remainder of the second term on the right hand side. So that is your E of X divided by your G of X. So if this term does not have any remainder, that will give you a syndrome equivalent to 0. So either E of X is 0 or E of X is divisible by GX. So we don't have to worry about the first case if E of X is equal to 0. So that means there is no really an error. The second case is the more important. That means those errors that are divisible by G of X, okay, which are not caught. So we cannot detect them. So there are different there are different types of error, and let us show some specific error and see how they can be caught by a well-designed generator. Okay, so what should the structure of G of X to guarantee the detection of a first type single bit error? So a single bit error is represented by E of X, X raised to I, where I is the position of the bit. Okay, so if a single bit error is caught, then x of I is not divisible by g of x. Okay? So how do you do that? When we say not divisible, we mean there is no remainder. So how can we make sure, okay, how can we make sure that there is the generator can detect a single bit error? So it is if the generator has more than one term, okay, and the coefficient of x raised to 0 is 1. Okay, so if the condition is satisfied that the generator has more than one term and the coefficient of x raised to 0 is equal to 1, we can be assured that all single bit error can be caught or can be detected. Okay, how about this one? So, two isolated single bit errors. Okay, so this is represented by E of x equal to x raised to j plus x raised to I. So, it should be exponent. Okay, so the value of a and j define the positions of the errors, and the difference of j minus I defines the distance between two errors. Okay, so now imagine that there are two single bit isolated errors, so they are not consecutive. Okay, so they don't they're not side by side. Okay, so under what condition can this type of error be detected or be caught? Okay, so the condition is if the generator cannot divide x raised to t plus 1. Okay, so what is your t here? Okay, t is between 0 and n minus 1. Okay, so look at the figure. So n minus 1. Okay, so whatever the values there. So if the generator cannot divide x raised to t plus 1, so that means your t lies between a value between 0 and n minus 1, then all isolated double error can be detected. Okay? Next is odd numbers of errors. Okay, so a generator that contains a factor of x plus 1 can detect, okay, so we are guaranteed it can detect all odd numbered error. Okay, so this means that we need to make x plus 1 a factor of any generator. Note that we are not saying that the generator itself is x plus 1. No, because if our generator is x plus 1, it cannot catch two adjacent isolated errors. Okay, so for example, we have Okay, so for example, we have x raised to 4. So we have x raised to 4 plus x squared plus 1. Okay, so it can catch, so we are assured that it can catch all odd number errors, okay, because we can write this as what? So we can write this as x plus 1 multiplied by x cubed plus x squared plus 1. Okay, so it can be factored out as x cubed plus x squared plus 1. So therefore, when your generator has a factor of x plus 1, we can be assured of detecting odd numbers of errors. Okay? How about burst errors? Okay, so burst errors is considered as the most important of all. Okay, so burst errors is given by e of x equal to x raised to j plus that x raised to I. Okay, so uh, what is the difference between the burst error and the two isolated bit error? So the burst error can have two or more terms. Okay, so two or more terms, while the single two isolated single bit error can only have two terms. Okay, so that's the difference of the two. Um, we have here factoring out xi and writing the error as xi multiplied by xj minus 1 plus 1. So if a generator can detect a single error, then it cannot divide x raised to I. Okay? So those generators that divide x minus raised to j minus 1 plus 1 divided by x raised to r plus 1 must not be 0. Okay? So there are three cases to this. Okay? So what are those three cases to this? First case is if j minus I is lesser than r, okay, so the remainder can never be 0. So we can write j minus 1 is equal to L minus 1, where L is the length of the error. So L minus 1 is less than r, or L is less than r plus 1. So this means all burst errors with lengths smaller than or equal to the number of check bits, okay, which is your r, will be detected. Okay, so those number of bits that are appended to your original data word. Okay, so in some cases, if j minus 1 is equal to r, um, or L is equal to R plus 1, so the syndrome is 0 and the error is undetected. So in some cases, when your J is greater than R or L is greater than R plus 1, the syndrome is also again 0 and the error is undetected. Okay? So to summarize this class, a good polynomial generator needs to have the following characteristics. Okay, so a while ago we said that a polynomial generator is already predefined and agreed upon. Okay, so how do you choose a good polynomial generator? So it must have this following characteristics. So it should have at least two terms. Okay, so the coefficient of the term x raised to 0 should be 1. It should not divide xt plus 1, wherein t is between 0 and n minus 1, and it should have a factor of x plus 1. Okay, so if our generator has this following characteristics, then the previous errors that we have discussed will be detected. Okay, any type of errors pertaining to them will be detected. Okay, so we have here standard polynomials. Okay, so these are some standard polynomials used by popular protocols for CRC, or cyclic redundancy checking generation, along with the corresponding bit pattern. Okay, so we have here CRC 8, CRC 10, CRC 16, CRC 32. So these are usually the standard, okay, or the recommended generator polynomials, okay, so to be used. So what are the what are the advantages of cyclic codes? Okay, so we have here different advantages of cyclic codes. So we have a very good performance. Okay, so in detecting different types of errors, so we have single bit errors, double errors, you have your an odd numbers of errors and burst errors. Okay, so they can easily be implemented in hardware and software, and they are especially fast when implemented in hardware. Okay, so this has made cyclic codes a very, very good candidate for many networks. Okay, unfortunately, we will not be including the hardware anymore, but in your higher communication subjects, you might happen to discuss how hardware is being implemented for these typical types of cyclic codes. Okay, so we are not yet done with error detection and correction. So this is just for the detection portion. So we will still be having a part 2 of this video, wherein in that case, we will be discussing the correction. So in the detection, we are just trying to figure out whether there is an occurrence of an error. Okay, so we are not yet correcting the error. So the next video will discuss the another type of error detection code, which is checksum, and at the same time, we will be discussing error correction techniques. Okay, so thank you very much for watching and have a nice day. Okay, bye.